Hi everyone. So let's continue where we left off. So we had introduced the idea of the proof of the following result, which tells you that every integer is a product of primes. So the main idea really depends on the fact that that every number is an increment of 1. So there is no jumps over in integers. So that's the main core idea, and it's captured by the well ordering axiom. So let's see how can we prove it. So how we can prove it is by first knowing that if n, so let's see how we can prove it. So first we can focus on integers who are positive, because if they are, if we can factor the positives into prime, so that means that we can take the negative twice to arrive that we can also factor the negatives into primes. So let's see the reason. Yeah, so first note, if n is negative and the result holds for positive integers, then you can take the negative n, which is positive, so it can be factored as products of primes. So that means that negative of negative n is negative of p1 multiplied by other products of primes. And so we have proven also that we can also write the negative integers as products of prime, assuming that we prove that the positive integers can be factored into product of primes. So let's prove the result. Yeah, so let S, so assume that n is greater than 1, and let S be the set of integers greater than 1 that are not product of primes, So we will show that S is non-empty. We will show that S is empty, not empty. So that means there are no integers greater than 1 that is not a product of primes. So every integer is a product of primes. So let's do that. So first we assume that S is not empty and let T be the minimum element of S, which is guaranteed to exist, by the well-ordering axiom. Okay, so T is inside of S and T is not prime. So since it is not prime, then it means that it has two factors other than 1 and itself that goes precisely into M. So that means that T can be factored as A, B with 1 is less than A is less than T, and similarly 1 is less than B and it is less than T. So since A and B are integers and they are greater than 1, so that means that it cannot be less than S. So it cannot be less than S. So in particular, it must be elements of it cannot be elements of S. So in particular, as it is less than T, so in particular we have that they are products of primes. So A is a product of prime and B is also a product of prime. As we have that A and B are less than T. So in particular, we have that T is P1 to PR, Q1 to QR, so is a product of primes, which means that T is not an element of S. So we found a contradiction. So that gives us a contradiction, and so S is empty. So S is empty, and we are done. All right. So in the next video, I'll prove the fundamental theorem of calculus, not calculus, arithmetic. I'll prove the fundamental theorem of arithmetic, and we will move on from there. See you guys.